Hello all. You may remember a little while ago I posted a video called "Has the Speed of Light Been Broken?" which can be found in the comment in the description below. This was talking about a paper that was published as of 2016 in the Plasma. Well, basically a J in the journal JETP Letters. Well, the reason why I brought this up is because of the fact that it seemed to suggest that there might have been an upper speed limit of 1.7 C for gravitational waves. Now, I recently watched a video by PBS Spacetime, really good people. I'd recommend you check them out. Their video is also in the description below, which was talking about how the speed of light is actually the speed of causality, and this is the maximum speed that anybody can, or that anything can travel, including massless particles, due to causality reasons via the Lorentz transformation. So I actually went to Facebook and asked them about how to address the apparent odds between theory and experiment. But so basically what happened was I asked them about whether or not there was a apparent contradiction between the two. And somebody pointed out that the 1.7 C is the experimental upper limit that was found from that particular data set, the very first LIGO finding. They also recommended that that it was not, they did not actually measure that they were traveling at that speed. It was only highly unlikely that they were traveling any faster than that, and that experimentally and theoretically they seem to travel at C so far. So I thought we'd go back over that paper a second time and actually determine what's actually going on with that. So the paper goes on to say that they compare so they basically say that the speed of propagation, we point out that the observed time delay between the detection at the Hanford and LIGO sites from the gravitational waves places an upper bound on the speed of propagation at C of gravitational waves as being 1.7 C in units of the speed of light. Combined with the lower bound from the absence of gravitational Cherenkov losses by cosmic rays, rules out most subliminal velocities. Now let's actually go straight to the pulsar time, the model-specific constraints for pulsar timing, and upper limits from upper bounds from gravitation 1. There's clearly an interest in setting the upper bound on CGW. Let us recall this was not done since it was assumed that CGW equals 1, and the difference in the time interval signal due to the interferometers was used to localize the event. One can also take a different view. We use the fact that the two LIGO sites at Livingston and Hanford are separated by a distance of d equals 10 microseconds light travel time, and have detected the signal within the time shift of delta t equals 6.9 plus 0.05 and minus 0.04 microseconds. This time delay is equal to the projection of L of the inner site distance d on the direction of the perpendicular perpendicular to the gravitational wave, independently of the arrival of the gravitational wave. L cannot be larger than the intersite distance d itself, which is given by the bound. Substituting conversely gives the minimal value of delta t within 2 sigma deviation, and we get CG is less than 1.7. We have shown how our very naive interpretation of the analysis of the detection of GW sets the first direct bound on the speed of propagation of gravitational waves. This observation complements the lower bound coming from observations of high-energy cosmic rays. Our constraint is already interesting, yet very conservative. We believe it can be improved by considering other features of the event, such as the orientations of the detectors and the resulting antella patterns, the amplification of the waveforms, and the measured at the two sites, and or more information about the position of the source in the sky. We have also made the assumption that the change in the emission process as a result of the gravity would not affect the measurement of the time delay between the two waveforms significantly, even if it would affect the determination of the source parameters. One can envisage that the two approaches to relax this assumption. The first is to develop a numerical simulation, a complete numerical simulation of binary coalescence existing theories predicting C gravitational waves from 1. Alternatively, one can focus on just the propagation of the GW and implement a data analysis that would disentangle the measurement of the time delay from the model of the GW emission. We believe that the results obtained by pursuing both of these directions would be of great value to fundamental physics. So in other words, basically they found that it was an experimental upper limit, and it was independent of model. So basically what this seems to suggest is that there is a possibility. I'm just going through this to see, yeah, this is the conservative bound arising from generative. Note the lower bound. Here's something. There's no theoretical argument or pathology against signals propagating faster than light. Furthermore, these theories can provide a setup where gravity can potentially be quantized using the standard dimensional framework of quantum theory in 4 dimensions. Thus, a measurement of CGW is a concrete application of the LIGO results to test the ideas of quantum gravity. But anyway, basically what it looks like is that these upper bounds were apparently an experimental upper bound based on this data, and it only presents a possibility that the gravitational waves were going FTL. It's not actually showing that they were for certain going FTL. So further research is needed in this area, and basically for now, assume C propagation, but keep an eye on this and basically see how things develop. Anyway, that's been this video. Hope you guys enjoyed that, and we'll go on from there.